Welcome to lecture number 27 for ECE 341 Random Processes, student t-test with two populations. Now as a recap, what we've done previously in this course, we've looked at a normal approximation and a student t-test. A normal approximation assumes a single population where you know what the mean and standard deviation are. For example, if I take a six-sided die, I know what the mean and standard deviation are for a six-sided die. If I roll them, I can find out what's the probability that the sum of 10d6 is more than 39.5. To do that, I find the z-score, how far is 39.5 from the mean in terms of standard deviations, then use a normal table to find out what's the area of the tail. If I don't know the mean and standard deviation, I can collect data. When I do that, I estimate the mean and standard deviation from my data, but now that's a t-test. That's a student t-distribution. What a student t-distribution assumes is, again, a single population. I assume the distribution is the normal PDF, but instead of knowing the mean and standard deviation, I estimate them from n measurements. For example, if I have a bunch of transistors like 3904s, I can take those transistors, measure the gain of a bunch of them, and from that find out what's the probability the gain's more than 100, what's the probability the gain's between 100 and 300. I can do that for temperatures. For example, we have the June temperature in Fargo. I've got data since 1942. If I am playing the game of Hungry Hungry Hippo, I can record my data, record how many points I get for a couple different games. From that data, find the mean, find the standard deviation, and find out what's the probability that I'll score more than 100 points, 90% confidence interval for the data. Those are all student t-distributions. Now today we're going to look at what happens if you have two populations, such as I want to compare 2 months, June versus July. Which one's hotter? I've got two players playing a game of Hungry Hippo. Each player has a mean and a standard deviation. Who's going to win the next game? Who's going to win an infinite series? Or if I have transistors, I've got two batches of transistors, one from company A, one from company B. Is there a difference? Which one has the higher gain? Well, that's things I can do with two populations, A versus B. Now the problem I have is that a t-test is not designed for two populations, it's designed for one population. What I can do is change the problem. And this is kind of like my favorite story of the fire extinguisher and trash can. If you've had me in classes, you're going to hear the story over and over again. But the joke is this. I've got an engineer and a mathematician, and they're doing a study on them. So they bring the engineer into the classroom, put the fire extinguisher in the trash can, light the curtains on fire, and tell the engineer, douse the flames. Well, the engineer dutifully runs in, grabs the fire extinguisher out of the trash can, douses the flames. The guy doing the study says, not bad, not bad. Okay. Brings the mathematician into the room, puts the fire extinguisher on the desk, lights the curtains on fire, tells the mathematician, douse the flames. Mathematician runs in, grabs the fire extinguisher, throws it in the trash can, announces, previously solved, then walks out of the room. Now that, in a nutshell, is engineering. I've got a solution. I can do a t-test with a single population. What happens when I have two populations? Well, if I can turn two populations into one population, I've got a solution, previously solved. Use the previous solution. That's what we do with two populations. If I have two populations A and B, I'll create a new population W that's A minus B. Now when I take the difference in the two, if A is a normal distribution, B is a normal distribution, then the difference also is a normal distribution. That's the central limit theorem. Now the mean of A will be, or the mean of W is just the mean of A minus mean of B. The variance of W will be the variance of A plus the variance of B. That's if I want to know about a single individual. If I want to know about the population, like who's got the higher average, then I take the variance of A for population, S squared A over NA, plus the variance of B for population, S squared B over NB. Add those together, that's the variance of W. So now I've got a single population W with a mean and a variance. Do a t-test, just like before. Now, anytime you do a t-test, I need to know the degrees of freedom. That's your sample size. The correct way to calculate it, this is from Wikipedia, is this kind of nasty formula, function of the degrees of freedom, a function of the sample size of A and B, the variance of A and B. Put that all together, I get degrees of freedom. What I do is just take the smaller of the two, the variance of A, or degrees of freedom of A, degrees of freedom of B, take the smaller of the two, that's the degrees of freedom of W. It's not exactly right, but gives you almost the same answer. It doesn't have a huge impact on the answers. And kind of one way to think about that. Suppose A has a sample size of infinity, then I know its variance exactly. All I really care about is B versus a threshold. In that case, the degrees of freedom of W is just the degrees of freedom of B. So the limit as sample size goes to infinity, it is just going to be the degrees of freedom of either A or B, the other one, the smaller of the two. Another way of thinking about it is if I have my data for A, data for B, take each data point, take the difference. In that case, W has exactly the same number of elements as A and B. It's just the degrees of freedom of A or B, same thing. That's kind of what this does. Technically, you should use this formula. Personally, I just say, take the degrees of freedom of A and B. The smaller of the two is the degrees of freedom of W. Slightly conservative, but doesn't make a huge difference. On your homeworks, use either one. Now again, I've got to keep track of, am I talking about an individual or a population? An individual would be like two people are playing Hungry Hungry Hippo. Sometimes A has a high score, sometimes B has a high score. Who's going to win the next game? That'd be an individual. The probability of A winning goes to a constant. It doesn't go to 1 or 0, it goes to a constant. In contrast, if I'm talking about populations, then I do divide the variance by sample size. For population, I might be asking, I've got two populations, who has the higher overall average? That overall average is the population. If the two players play an infinite series, who's going to win? In an infinite series, if A is slightly better than B, A will win the infinite series, even if it's just a very, very small amount. A small advantage will eventually determine the winner in an infinite series. In those cases, the sample size does affect the odds, and so there I do divide the variance by the sample size. And kind of what it comes down to is if the sample size is large enough, I can identify a very, very, very small difference in the two. I'm going to do a couple examples in this lecture. One will look at temperatures. Let's compare two different months, like July versus August. Which month is warmer? Let's look at two 20-year time spans. Is the last 20 years warmer than 1950 to 1970? I collect transistors. I've got two batches of transistors. Does one batch have a higher gain than the second batch? For capacitors, take a polyester capacitor and flip it, change the polarity. Does that affect capacitance? Does temperature change the capacitance for a polyester film capacitor? Those are things I'm going to look at. These are two populations, correct polarity, incorrect polarity, temperature 1, temperature 2. So let's start out. If I go to Hector Airport, Hector's been measuring temperatures in Fargo since 1942. If I look at the month of July versus August, I've got 81 data points in July, 81 data points in August. Here's the mean, here's the standard deviation for the high, for the average temperature in July and August. And here's what the PDFs look like. Okay, assuming a normal distribution, here's the distribution for August, distribution for July for the average temperature. Let's compare the 2 months. Well, a couple ways to ask the question. I could ask, this coming year, will July be warmer than August? Now that's an individual question. It's not guaranteed. I could have a cool July, I could have a warm August. On average, July is warmer than August, but on any given year, it's not guaranteed. So since this is an individual, I don't divide the variance by the sample size. I just calculate a new variable w, this a minus b. When I do that, I take the difference in the means. The difference in the mean is 1.95. I add the variance. Again, you don't subtract, you add. Kind of the reason is the variance is measured the spread. I could have a warm July, I could have a cold August. The spread is going to get bigger. So the spread getting bigger means the variance adds. So add the variance, take the square root, I get 3.67. And degrees of freedom is a nasty formula, add the two together. You actually get 159.61 for degrees of freedom. I would just take the smaller of the two. 80 and 80, the smaller of the two is 80. If I took each year and subtracted them and created a new variable w, I'd have 81 data points, 80 degrees of freedom. Another way to analyze it. Again, I would say I have 80 degrees of freedom. It doesn't have a huge impact on your homeworks. Use either one. I would take 80. Some people use 159. It really doesn't affect the odds. Next, find the t-score. So if I take w, back over here, the mean is 1.9, standard deviation is 3.67. So the mean is 1.9. This is a minus b, July versus August. On average, July is warmer than August by 1.9 degrees. This is 0 degrees. This area right here is the probability that July will be warmer than August. This area over here is the probability that July will be colder than August. I want to find this area. I want to find the area to the right of the tail. So go to StatTrack. I have a t-score of 0.5330. I have 80 degrees of freedom. Find the area to the right. It's 70.22%. And to kind of illustrate that, go to StatTrack, 0.5330. I have 80 degrees of freedom. My t-score is 0.53220. I'm using a plus number because I want the probability bigger than 1. Area of the tail is 70.19%. Now if I were to go back and use the correct calculation and say 159 degrees of freedom, 70.23%. Again, that doesn't have a huge impact on the results. Second question, which month is hotter, July or August? Now that's a population question. One of the 2 months is actually warmer than the other. I don't know which one. I have a limited set of data. But as the data set gets to infinity, I'll eventually be able to tell a very, very small difference. So since this is a population question, I do divide the variance by sample size. So when I do that, I've got the standard deviation of July, square it, get the variance, divide by its sample size, 81. Variance of August, divide by its sample size, 81. Add the two together, take the square root. Now it's 0.4. Degrees of freedom, again, is technically 159. I take the smaller of the two, 80. Now find the t-score. How far is the mean of w from 0 relative to its standard deviation? It's 4.79 standard deviations away. Go to a t-table with 80 degrees of freedom. T-score is 4.79. I get 99.999%. What that's telling me is that any given year, July could be colder than August. Usually it's warmer. But overall, July is warmer. This distance right here, the distance between the means, relative to the standard deviation in the sample size, is 4.79 standard deviations away. Meaning that there is a statistical significantly difference between July and August. I can see that difference. On average, July definitely is warmer than August. Well, 99.999% certain that July is warmer than August overall. As sample size goes to infinity, I can see a very, very small difference. Again, this is where the word significant has a different meaning in statistics than English. In statistics, significant means, can I tell the difference? Here, this is the average temperature in August, average temperature in July. I can definitely see there's a difference. Colloquial English means, do I care? Again, this is 71 degrees versus 69 degrees. Not a huge difference. I may not care. That's colloquial English versus statistical significant means I can see the difference. Let's take a different problem. Now, if I go back to the data set from Hector Airport, I've got data since 1942. Got warm years, cold years. Let's just take the first 20 years of data, compared it to the last 20 years, or 21 years. Is Fargo getting warmer? Is the last 21 years warmer than the first 21 years? If I do that, grab the 21 years of data, find the mean, find the standard deviation, degrees of freedom, and sample size -1. Compare these two populations. So here's what the PDFs look like. This is a normal distribution centered at 40 degrees, spread of 1.6. Standard deviation, or normal distribution, centered at 42.9 degrees, standard deviation 2.05. On average, B is warmer than A. Now, when I test this, it depends upon what I'm talking about, an individual or population. Now, if I pick a year at random from population A versus B, will that one year be warmer? To do that, I form a new variable W, that's A minus B. The mean is the mean of A minus mean of B, minus 1.9. The variance is add. So here's what it looks like. I've got a bell-shaped curve, normal distribution. This is W. The average is minus 1.98 degrees. And here's 0. 2.65 standard deviations away. So this would be the chance that a given year in the first decade, 1940s, is warmer than the current last 20 years. Not likely, but could happen. To find out this area, or the area of the tail, I'll do a t-test. Now that I have a single population, a t-test works. So what I'll do is I'll find out how far is the mean of W from 0 in terms of standard deviations, or for A and B. How far is the mean of A from the mean of B in terms of combined standard deviation. It's 0.74 standard deviations away. Got a stat track. I've got 20 degrees of freedom, roughly, smaller of the two. T-score of 0.74 means the probability is 23%. So there's a 23% chance that a year in the first 20 years will be warmer than the last 20 years. And there's quite a bit of overlap. I could have a warm A as cold B. 23% chance A will be warmer than B. It's not 0. Population question. Is the average of the last 20 years warmer than the average of the first 20 years? Is something changing? Well, to do that, to find the standard deviation of W, or the variance of W, I'll take the variance of A divided by sample size of A, plus the variance of B divided by its sample size, add them together. Take the square root to get the standard deviation, we get 0.29. So now what it looks like, mean of W is still minus 1.98. The standard deviation is 0.229 degrees, and so 0 degrees is way over here, or 0 difference. I want to find the t-score. How far is the mean from 0 relative to the standard deviation? Or here's the equation spelling it out. It's now 6.7 standard deviations away. So these are definitely very different. The mean of A is definitely lower than the mean of B. That means it can be 99.999% certain that the last 21 years is warmer than the first 21 years. That's population versus individual. You know more about populations than individuals. So again, this is saying that it's most likely 99.999% certain that Fargo is getting warmer. Note this doesn't tell you why it's getting warmer, it just says that it is. Again, a lot of reasons it could be. The planet's warming up, CO2 levels are going up, ice is melting. Another reason is the city of Fargo is growing. As cities grow, they have more asphalt. You cut down trees, pour more asphalt. Asphalt is warmer than green grass and trees. It's pretty well documented that cities are warmer than countryside. So it could be that Fargo is growing. It could be some other reason. It could be a combination. And the t-test doesn't tell you that. It just says that, yes, Fargo is getting warmer. I can see it. So once I have t-tests, I can start asking some interesting questions, such as, are polyester film capacitors polarized? If I put them in a circuit backwards, does it make a difference? Are electrolytic capacitors polarized? Does temperature affect the capacitance? I could do other questions, like, do loud noises affect my reaction time? Are they affected by 1 or 2 drinks? Does alcohol-free gas improve my gas mileage? Does adding a lid to a cup of coffee keep the contents warm? Does adding a spoon make a difference? Lots of things you can ask. With a t-test, I can start answering those questions. So here we're just going to look at 3 examples. Are polyester film capacitors polarized? Does temperature affect them? Get 2 questions. So the first thing I need is data. I'm going to take a polyester film capacitor. So here's what they look like. If you ever see these in the lab, those are polyester film capacitors. They don't have polarity marked on them. Should they? Is there a difference? Put them in the circuit one way, flip it around, put it the other way. Does that make a difference? Well, to do that, I first have to take data. I'm going to measure the capacitance of 10 polyester film capacitors. Measure the capacitance with the correct polarity, flip them around, measure the capacitance again with the incorrect polarity. Given that data, I've got a mean, I've got a standard deviation. That's for 2 populations, A and B. To compare them, I take the difference in the 2, create a new population W, this A minus B. So here's the difference between A and B. Find the standard deviation. For an individual, I don't divide the variance by the sample size. Population, I do divide the variance by the sample size. And degrees of freedom, and take the smaller of the 2, 10. Now for analysis, I'll form a t-score. That's the difference, the mean of W versus 0, divided by the standard deviation W. If I do that for an individual, I get a t-score of minus 0.02, meaning 49% probability A is greater than B. Populations, I take the t-score divided by the population's standard deviation. T-score is 0.06, probability is 47%. But plot the 2 PDFs. Blue is the forward polarity, red is reverse polarity. That's what PDFs look like. Basically, they're the same. So that tells you that polarity really doesn't make difference on polyester film capacitors. Use them either way, doesn't make a huge difference. There's actually a couple ways to analyze this data. This is where when you collect data, it pays to keep the raw data. So rather than just tell you the mean standard deviation, if I kept the raw data, here's another way to analyze it. For each capacitor, I've got the capacitance correct polarity, incorrect polarity, take the difference. This is for the first one, second one, third one, fourth one. I can do that if I have the actual data. If I lose the data, I just have to use the mean standard deviation. Here's if I have the actual data, the difference for each one. Take those differences, that as a mean standard deviation. Now using this data, analyze it. For an individual, the t-score is how far is the mean from 0 relative to standard deviation. It's minus 2 deviations away. And the probability is 3%. That's the area of the tail, or 97%, or the main part. So that kind of says an individual, 97% chance that it has smaller capacitance with correct polarity, higher capacitance, incorrect polarity. For the population, it's 6.49 standard deviations away. the area of the tail is 0.00006, or I'm 99.994% certain that polarity makes a difference. And this is where statistical significance is different than colloquial English. Colloquial significant. The difference in capacitance is 2 nanofarads. The actual capacitance is 384 nanofarads. What this means, statistical significant means, if I analyze it this way, I can see the difference. It is there. There's about a 2 nanofarad difference when I flip the polarity. Colloquial is, do I care? 2 nanofarads out of 380, that's 0.5%. I really don't care. But statistical significance means I can see it. This is also where how you analyze the data makes a difference. If I keep the actual data, I can analyze it a different way, take the difference in each capacitor, and see what the difference is. If I do it that way, I can see the difference. If I just look at the overall population's mean and standard deviation, no, I can't see the difference. I get actually different answers depending on how I analyze the data. Let's look at electrolytic capacitors. So this is what electrolytic capacitors look like. They've got a little marking as to what the negative lead is. These are polarized. Let's see if it makes a difference. I'm going to pick a 1 microfarad electrolytic capacitor, this one type from one vendor. See if that batch of capacitors is polarized. They are marked, so I expect that they are. Let's measure it, see if they are. So I'll measure the capacitance with the correct polarity, capacitance incorrect polarity. Each one's got a mean, standard deviation. I'll also keep track of each capacitor separately. For each capacitor, take the difference, correct and incorrect, see what the answer is. That too has a mean and a standard deviation. Now the answer I get depends upon how I analyze it. If I use the population data, I've got the difference in the means, the variance added together, the t-score, probability, and here's forward correct polarity, incorrect polarity. This says the capacitance actually got higher with the incorrect polarity, not by a lot. If I pick a random capacitor from population A versus B, 46% chance it'll be smaller with A than B. That's basically coin flip, 50-50. Small difference, but not much. If I go populations, there's a 40% chance A will have a higher capacitance than B. Again, basically a coin flip, 50-50. That kind of says that polarity doesn't matter for this patch of electrolytic capacitors. If I look at the difference in the two, then it's got a mean of minus 1.38, standard deviation 0.7, t-score 1.97, meaning 3.9% chance for an individual. 97% of the time, incorrect polarity's got higher gain than correct. For the population, it's 99.993% of the time, incorrect has a higher polarity than correct. So this kind of says that the electrolytic capacitors I'm using, polarity does matter. I can see the difference if I analyze the data separately, meaning for each capacitor, take what it is correct polarity versus incorrect. Incorrect capacitance actually goes up on average by 1.3 nanofarads. There's a W distribution saying this is definitely left of 0. I can see that. So if I analyze it on an individual basis, take each capacitor's correct, incorrect polarity, take the difference, I can see that difference right there. Another question. Does temperature affect polyester film capacitors? Again, I'm going to measure the capacitance at 83 degrees Fahrenheit. That was the temperature of my office one day last year. Throw them in a refrigerator, then measure the capacitance. Does that 40-degree difference change the capacitance? So again, what I need is data. I'll measure 10 capacitors at 83 Same 10 capacitors at 40. Each one's got a mean, standard deviation, analyze as a lump sum. I also kept track of each capacitor and take the difference between the two. Depends why I analyze them. We use the population's mean standard deviation. I get a t-score, and 85%. There is a difference. Capacitance actually goes up with temperature. And I can see it, 85% likely the warmer capacitors have a higher capacitance. If I analyze each capacitor separately, the difference between 83 and 40 degrees, take this data right here, it's got a mean standard deviation. That gives me this distribution. Find out, is that higher than 0? And there I can tell you that, yep, for the population, I'm 99.9999% certain, or t-score is 31. That's a huge t-score, saying yes, absolutely, temperature does affect capacitance. Again, this is statistically significant. The capacitance went up by about 2 nanofards when I warmed it up. Statistically significant means I can see that difference. Colloquial English significance is, do I care? Again, this is a 1,000 nanofarad capacitor, went up by 2 nanofarads. Is that a big deal? Probably not. But that's the t-test with 2 populations. With the t-test, I can compare 2 populations. The t-test is really designed for a single population, but if I do this trick, I create a new variable w, this a minus b. I now have 1 population. With 1 population, I can do a t-test. What I'm really doing is I'm checking is w greater than 0, is a greater than b. Kind of a sidelight, when you collect data, keep all your data. Don't just tell me the mean, standard deviation, sample size. If you keep all your data, that opens up possibilities. There are other ways to analyze your data. And the answer you get depends upon how you analyze the data. For example, here, if I kept the individual capacitors and took the difference, I can see that each one is actually shifting as temperature goes up. As I flip the polarity, I can see that difference on an individual basis. If I just lump all the data together, say I've got a mean, standard deviation, that information might be lost. Another thing to note is that this only works with 2 populations. With 2 populations, I can take a minus b and create 1 population. If I have 3 populations, I need a different tool. And there are tools for that, for example, analysis of variance, later on this semester. But a t-test really isn't designed for more than 2 populations. That's lecture number 27 for ECE 341. Our next lecture will do a couple more examples of t-tests with 2 populations.